Okay, here we're going to briefly talk about arrays in Python. Array being a collection of numbers. Python does not have native support for arrays, which is less than optimal for scientific computing. However, there is an excellent third-party array package for Python called NumPy, and there has been a whole stack of software that has been built up on NumPy. And while it's not native to Python, it is very integral to most scientific uses of Python and comes uh, distributed with the Anaconda package that you've installed. A little bit of history here, but the main point is that NumPy will be the backbone of much of what we work on in this class, and we will cover in more detail a lot of the characteristics of NumPy arrays after we talk about collections in our next module. But just to get started with it, since we're talking about numerics, let's explore it here. So first off, commonly NumPy is imported with the synonym NP. So this is something that we can do with all packages that we import in Python. We import NumPy as NP, and this is how you'll typically see it in most applications. So NumPy arrays are collections of numbers that can be manipulated efficiently together as a collection. Different than most other things that we'll do in Python, the arrays have a type that specifies what the underlying representation of the number is. So whereas in with floats and ints, we don't declare a variable as being a float or an integer. It comes out in how we're typing it. In NumPy, we need to specify what type of underlying numeric representation we're going to be using. And so for the integers, there we can either have 8, 16, 32, or 64, probably even 128-bit integers. But you see, for every one of those, we have a U, meaning unsigned, and a without a U, which means, so I got a typo here, this should be signed integer representation. And so this is basically saying, okay, I have 8 bits, and I'm going to use all of them for representing the magnitude of the number, versus here I have 8 bits, but one of those bits is going to be used to represent a positive or negative. And so in the unsigned int 8 case, the largest number I can represent is 255, whereas in the signed, because I only have 7 bits to represent the number, it'll be 127. And the more bits I allocate to representing my number, of course, the larger the number I can represent. So what's up with these different types? So you have the question of memory allocation. So if you have a very big array, memory constraints might come into play. And so why allocate 64 bits for every number that you're going to represent when you know that, say, the largest value will be 1. It's like a binary image, 0 or 1. Or that you read in a JPEG image and the largest value is 255. So if memory issues come into play, then you want to use the fewest number of bits to represent the numbers that you have. Now there's computational efficiency. So one of the reasons that integers by default in Python are 64-bit is that it's most efficient to use the representation that matches the underlying architecture of your computer. So it's actually faster to work with a 64-bit integer than it is a 16 or a 32-bit integer. And so there's a trade-off there between the memory allocation and the underlying efficiency of the computation. So here's how we would create an array. So NumPy comes with an array function, which takes some sequence or collection In this case, this is a list of two numbers, negative 128 and 127. And I can optionally specify what data type I want to use. In this case, I'm going to say make these signed 8-bit integers. And down here, I'm doing a similar thing, but I'm going to tell it to make it an unsigned 8-bit integer. So let's see what happens. So it didn't complain. We're providing a -1, which is, but we're saying it's an unsigned integer. And so Python, if this is consistent, it may not be what you expected, but it recognizes that -1 is 255. And that's because that bit there that's being used for the negative number is being interpreted not as a sign, but as the a numeric value. So being aware of this is important. You can get some funky, unexpected behaviors, like you're expecting -1, you got a 255, so you got to be aware of that. And just like there's a variety of different integer types of arrays, we have a variety of different choices for the floating point arrays that we're going to use, or the complex arrays. You see the complex are double the size of the floats. That's because you have a floating representation for the real part and a floating representation for the imaginary part. And so this is adding up the total number of bits that are being used to represent the number. So NumPy arrays, in addition to the data representation that you specify, have shape. And so here we created our variable b here, which has the value 255 and 2. And so characteristics that Python knows about these arrays are the number of dimensions and the shape. So in this case, the number of dimensions is 1. It's essentially a vector. And we have 2 elements. And that's the shape. So we can make, in addition to these one-dimensional arrays like we've done here, we can make 2-dimensional arrays, 3-dimensional arrays, so on. I think there actually is a hardwired limit to how many dimensions you can have in an array, but it's large. And so again, here we didn't specify what data type to make the array. And so Python chooses what it views as a sensible choice. So it recognizes these are all integers. And so it's using the int64. Okay, so that's driven by the underlying architecture of your computer. We can, once we've created an array, in this case we've created an A range, just takes the numbers from 0 to n-1, so this will be 0 through 26. This would be a one-dimensional array, but I can reshape it into a 3-dimensional array as long as the total number of elements match between the reshaped array and the original array. So in this case I took a one-dimensional array that would have been the numbers 0 through 26, and I'm reshaping it into a 3x3 array, which is printed out here. Arrays can be added together provided their shapes match, and also we have operations applied element by element. So here I have created the array D, and this notation right here indicates that every element in D is going to be squared. Here I'm going to square every element, and then I'm going to add D back to itself. And here, see, we've got C, which is a 2x2 array, and we're going to try to add that to our D squared. So let's see what happens here. So we can do the squaring, we can square, and then we can add D. But when we try to take D squared and add C, we get a value error because the shapes don't match. So this is just a very quick introduction. There's actually a nice tutorial that you can get an IPython notebook from, and we will delve into a lot more the details of working with arrays in our next group when we talk about lists, tuples, and dictionaries, etc.